Imagine holding a single, perfectly balanced coin. You flip it, and it lands on heads. At the exact same instant, billions of light years away, another coin spontaneously flips itself and lands on tails. There are no wires connecting them, no signals passing between them, and no predetermined instructions hidden within their metallic cores. Yet their fates are perfectly, instantaneously linked. This is not magic, nor is it science fiction. It is the fundamental reality of our universe at its most microscopic level. This phenomenon is known as quantum entanglement. It occurs when two or more particles interact in such a way that the quantum state of each particle cannot be described independently of the state of the others. They become a single, unified system. Even if you separate these entangled twins by the width of a galaxy, measuring the spin, position, or momentum of one will immediately dictate the corresponding property of its partner. The vast expanse of space between them simply ceases to matter. Such a bizarre reality deeply troubled the greatest minds of the 20th century. Albert Einstein famously derided this phenomenon as spooky action at a distance, finding it utterly incompatible with his theory of relativity. According to Einstein, nothing could travel faster than the speed of light, not even information. The idea that two distant particles could coordinate their states instantaneously seemed impossible, suggesting either a fatal flaw in quantum mechanics or an incomplete understanding of the universe. Investigating this paradox became one of the most profound historical challenges in modern physics. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, formulated the EPR paradox. They argued that the particles must contain hidden variables, secret internal blueprints established at the moment of their creation, which dictated their future behavior. To them, the universe was deterministic. The particles only appeared to communicate instantaneously because their coordinated outcomes were preordained from the very beginning. For decades, this debate remained purely philosophical, a clash between the deterministic comfort of classical physics and the probabilistic weirdness of the quantum realm. Then came a brilliant theoretical physicist named John Stuart Bell. In 1964, he formulated Bell's theorem, a mathematical proof that provided a way to test whether the universe relied on hidden variables or if quantum mechanics was truly as bizarre as it seemed. Bell devised an inequality that, if violated by experimental data, would definitively rule out Einstein's hidden blueprints. The theoretical gauntlet had been thrown down, but it required an experimental genius to pick it up. In the early 1980s, French physicist Alain Aspect conducted a series of groundbreaking experiments that finally put Bell's theorem to the test. By firing entangled photons in opposite directions and rapidly switching the measurement settings while the particles were in flight, Aspect closed the crucial loopholes that had plagued earlier attempts. The results were undeniable and earth-shattering. Aspect's measurements violated Bell's inequality. The hidden variables did not exist. The spooky action was real. This meant that the universe was fundamentally non-local, a concept that shatters our intuitive grasp of how reality operates. A measurement performed in one laboratory literally and instantaneously influenced the physical reality of a particle in another, bypassing the speed of light entirely. The entangled system acted as a single entity, undivided by the vastness of physical space. To truly grasp the magnitude of this, we must let go of the classical world where objects exist in isolation. The entangled particles continued their silent dance, indifferent to the miles of optical fiber or the vacuum of space separating them. It implies a deep, unseen interconnectedness woven into the very fabric of existence. The boundary between here and there dissolves, revealing a cosmos where distance is merely an illusion constructed by our macroscopic senses. This profound interconnectedness is not just a laboratory curiosity, it is a feature of the cosmos itself. Consider the extreme environments of the early universe. In the first fraction of a second after the Big Bang, all matter was condensed into an unimaginably dense, hot point. Particles interacted intensely, inevitably becoming entangled. As the universe expanded, these primordial connections were stretched across billions of light years. The cosmos we observe today might be saturated with a web of ancient, ghostly links. Harnessing this bizarre reality has transitioned from a philosophical debate to an engineering race, fueling the future technological promise of our era. The most prominent frontier is quantum computing. Unlike classical computers, which process information in binary bits of zeros and ones, quantum computers use qubits. These qubits can exist in a superposition of multiple states simultaneously, but their true power is unlocked through entanglement. When qubits are entangled, the computational power of the system scales exponentially. A classical computer must evaluate every possible solution to a complex problem sequentially. An entangled quantum processor, however, can explore a vast multitude of possibilities at once. The linked qubits calculate as a unified whole. This architecture threatens to render our most advanced supercomputers obsolete, offering solutions to problems in cryptography, material science, and synthetic biology that would currently take millions of years to solve. Beyond computational supremacy, entanglement holds the key to an unhackable future. Quantum cryptography, specifically quantum key distribution, utilizes the fragile nature of entangled states to secure information. If an eavesdropper attempts to intercept or measure an entangled photon transmitting a cryptographic key, the very act of observation collapses the quantum state. The interference immediately alerts the legitimate users to the breach. This absolute security is guaranteed by the fundamental laws of physics, specifically the no-cloning theorem. It is impossible to create an identical copy of an unknown quantum state without destroying the original. Therefore, the entangled link cannot be cloned, spoofed, or silently monitored. The spooky action ensures that the communication channel remains pristine, offering a technological promise of absolute privacy in an increasingly interconnected and vulnerable digital world. The leap from theoretical security to global infrastructure is already underway. In 2016, scientists launched MICIUS, a specialized quantum satellite designed to test entanglement over unprecedented distances. Orbiting hundreds of miles above the Earth, MICIUS successfully beamed entangled photon pairs to ground stations separated by over 1,200 kilometers. The ghostly connection held true through the atmosphere and the vacuum of low Earth orbit, proving that non-local reality is robust enough to span continents. This successful demonstration forces us to confront a startling implication about the architecture of spacetime. If particles can communicate instantaneously regardless of the distance between them, what does that mean for space itself? Some theoretical physicists propose that entanglement might be the very thread that stitches the fabric of reality together. Without these microscopic quantum links, spacetime might simply disintegrate into an incoherent mess of disconnected points. This radical idea is encapsulated in the ERR-EPR conjecture, a theoretical framework proposed by Juan Maldacena and Leonard Susskind. ER refers to Einstein-Rosen bridges, commonly known as wormholes, which are hypothetical tunnels connecting distant regions of spacetime. EPR refers to the Einstein-Podolsky-Rosen paradox of quantum entanglement. The conjecture boldly suggests that these two seemingly disparate phenomena are actually the exact same thing, just viewed at different scales. Under this model, two entangled subatomic particles are connected by a microscopic wormhole. The instant correlation we observe is not a signal traveling faster than light through normal space, but rather a profound geometric shortcut. The particles are literally adjacent to one another within the higher dimensional bulk of the universe. If this theory holds true, it bridges the agonizing gap between quantum mechanics and general relativity, suggesting that quantum entanglement generates the geometry of space-time itself. Imagine the universe not as a vast, empty stage where events unfold, but as an infinitely complex tapestry woven from quantum threads. Every time particles interact, a new thread is spun. The physical distance we perceive with our human senses is merely an emergent property, an illusion cast by the deep underlying network of entangled states. Reality is far more fluid, far more deeply connected than our macroscopic experience could ever reveal. Yet, for all our theoretical advancements and experimental triumphs, the core mystery remains fiercely resistant to simple explanation. We can mathematically describe how the linked particles behave. We can build incredibly sensitive instruments to measure their correlations. We can even harness their weirdness to build revolutionary technologies. But the fundamental why and how of the spooky action still eludes complete human comprehension. This enduring mystery highlights the profound limits of classical intuition. The human brain evolved to understand objects that have definite positions, definite speeds, and clear localized interactions. We are creatures of the macroscopic world, accustomed to cause and effect playing out at speeds slower than light. Quantum mechanics demands that we abandon these evolutionary prejudices and accept a reality that is fundamentally alien to our daily experience. Even biological systems might not be entirely devoid of this quantum weirdness. The emerging field of quantum biology investigates whether entanglement plays a role in macroscopic biological processes. For instance, The navigational compass of certain migratory birds, like the European robin, is suspected to rely on entangled electron pairs within their eyes. These delicate quantum states might allow the birds to literally see the magnetic field of the Earth, utilizing non-local physics to guide them across thousands of miles. As we peer deeper into the 21st century, the exploration of this non-local reality will undoubtedly accelerate. Researchers are currently striving to build a global quantum internet, a network of entangled nodes that will transmit quantum information across the planet with zero latency and perfect security. This infrastructure will not merely upgrade our current internet, it will fundamentally transform how humanity processes and shares reality itself. Looking back at the historical journey, the transformation of this concept is breathtaking. What began as a desperate attempt by Einstein to prove quantum mechanics incomplete has instead become the ultimate vindication of the theory's strangest predictions. The very phenomenon that was supposed to be the fatal flaw of quantum physics has instead become its most defining and powerful feature. The universe, it turns out, is not a collection of isolated billiard balls bouncing off one another in the dark. It is a deeply entangled web of relationships, where the state of a single particle can reflect the state of another across the cosmic void. The illusion of separation is a trick of scale, a limitation of our physical senses masking the profound unity of existence. We are standing at the precipice of a new era of understanding. The spooky action at a distance is no longer a paradox to be feared, but a fundamental truth to be embraced. As we continue to decode the invisible threads that bind the cosmos, we are forced to realize that reality is far stranger, far more beautifully complex, and far more interconnected than we ever dared to imagine.